All right, cool. So I guess I'll just repeat every question everyone asks so that people on Zoom can hear us. All right, so SETI. Not working now. Wait a second, sorry. That's working. Okay. So this is we're searching for intelligence that's beyond Earth. But first, what is intelligence? Right? A lot of people say octopuses are intelligent because there are videos on YouTube. If you just put them in a jar or put them outside the jar and put some food in the jar, they'll open the jar, pick the food out, and half of them will just close the jar. So they're pretty smart and they know how to get food. So what is intelligence? In SETI, we define intelligence as just the ability to make technology. Because otherwise, we can't really search for octopuses beyond Earth. But if you're just sitting on the top of the ocean and then you can't even find octopuses down there. So we're just looking for technology. So that's why SETI, S-E-T-I, also has other names like SETEE, where EE means electrical engineers. Yeah. So SETI is search for signs of technology in space that are not built by us. So, and this science of technology is called technosignatures. Many of you might have heard about biosignatures. So technosignatures is a kind of biosignatures because it can indicate past, present, or maybe future biology. Right. So, and there's a jargon term called ETI. It's extraterrestrial intelligence. We want you to use this term instead of aliens or little green men or any other ET terms that you use. So ETI is the formal term in this field. And do you have a question?
Sure.
Cool. So that's SETI. And modern SETI began with this realization that humans can communicate with ourselves across interstellar distances. In 1959, Cocconi and Morrison, they found out that you can use an 80-meter dish with a 200 watts per hertz flux density to communicate with ourselves across interstellar distances, and you can use the same dish to detect it. 200 watts per hertz, that was really a challenge in their time. But nowadays, it's not. Like, you can easily do this. And a lot of our telescopes, radio telescopes, can actually send signals that can be detected parsecs away, or even hundreds of parsecs. In 1961, there's this thing called optical masers, because the word lasers, it wasn't invented yet. So they knew about masers in the microwave and radio, but what's the equivalent in optical? Well, optical masers, right? So they were saying that you can send optical masers across interstellar distances and detect them. So Schwartz and Towns, they did the calculations and they showed that you can use a 10 kilowatt laser on a space-based 5-meter dish. So that's pretty big. That we don't even have do we have a 5-meter space telescope? I don't think so. It's probably like 3, maybe we have 6. Yeah. So it's like in the future, basically. But you can also do a ground-based 25 tiny telescopes or transmitters, like that big. And you can do the same thing. And nowadays, it's really within our technology to send this signal and detect ourselves. So that means we can send the signal to space if we want to and talk with aliens. And somebody actually did that. So the Arecibo message in 1974, they sent this huge message in binary code to the globular cluster M13. They weren't trying to communicate with aliens because, it's a globular cluster. So basically, we don't think there's any habitable planets in there. And they actually miscalculated their pointing direction. So imagine this. If this is M13 as you're seeing now, and you see some proper motion, and you know the light travel time, you send the light travel time plus proper motion times proper motion, or light times proper motion times 2.
You're getting
yes, because this is what you're seeing, and they're here right now. And that's where they'll be in the future. But they send it here. So luckily, they're not exposing our location, which is good. So they were demonstrating human technology, saying that we can use a 300-meter telescope to send a signal that's detectable across thousands of parsecs. But of course, the beam will be tiny, right? It's a huge telescope. I can get into the details of the message, but basically, if we were to intercept this message, I don't think we can actually decode it. If you didn't know what it actually means, because the binaries are expressed in a high frequency and low frequency with a hertz difference. I think it was 10 hertz. So first, you need that hertz-wide resolution, and then you're going to tell which is 1, which is 0. And just, what does this even mean? Right? You're going to send this signal in one line, and you're going to try to break it up into this rectangular thing and express them in 0 and 1s. So, yeah, first it tells you how to count and the elements that we use. So aliens or ETI, they can build their biological weapons and kill all of us. And then they talk about our nucleotides, so our DNA. So they'll have a better knowledge about who we are and design their weapons. And they also tell us how tall we are. Yeah. I think it was 1.76 meters or something. It's like average height of American men. Yeah, that's their understanding.
It's like C.
Yeah. And then they have like our solar system. That's the planets, that's the star, and that's where we are. So target your weapon in that direction. And that's a telescope that we're using. So like, can you see that's a telescope? Probably. Right. So we try sending messages. Yeah.
Sorry, how are they supposed to understand it? Like,
So they're assuming that aliens know about wavelengths. And
so
they're
it's-
expressing in terms of the wavelength of this message, the multiples of them.
If you use
What?
if you use metric,
I feel like in physical space, it doesn't matter. Like the wavelength will be that, and you multiply by 14, and it will be something. Yeah. Go ahead.
Who came up with what?
It was a bunch of, I think, astronomers, and maybe there were some humanity people involved. But I think it's all American people. And
Like, did they just do it in like a weekend?
let's take them all in here.
so I think they spent some time into this. But nowadays, I think this year or it was last year, 2023, we actually tried to decode the signal. And artists and a bunch of other people, they designed a signal and they transmitted that from Mars. I think it's called a sign in space or a sign from space. And SETI astronomers just try to decode it. We think that we'll never decode it, but we'll see. Yeah, so it's really hard to know what the message is. But when we detect something, we can say, there are people there. And then people will decode it. You know, if you watch Contact, the movie, there will be military people coming in. Maybe that's how it's gonna work. Cool. So nowadays, most SETI searches are based in radio and optical, and there's a reason. In radio, this is the noise levels. So the y-axis is the noise level, the x-axis is the frequency. So there's something called terrestrial microwave window. Just in that window, the noise is really low. If you go lower than that or higher than that, then the noise is really high, then you can't really see anything. And that's the frequency region that we look at, because we're ground-based. But when we go to space, like if you want to build a telescope on like moon, then you can do other wavelength. But for now, SETI searches are really just within like 1 to 10 gigahertz. Yeah, it's all instrumentation. But how can we tell between a SETI signal and a natural signal? So that's how broad optical masers are. And basically on similar scale, that's how wide the technological line is. It's hertz wide in comparison to like 10 kilohertz wide. So SETI is basically the search for unnatural things, like something that nature can never do. Because we know our emission lines have broadening mechanisms, and it will make the lines very broad. So in optical, it's the same. You have an optical emission line that's broad, but the laser line will be just really tiny, right? We've seen this in spectrum, I hope. A laser line will basically always be unresolved in a spectrogram, unless I think you need like millions for your resolution powers. Yeah, so radio and laser, we're just looking for this narrow thing. And that's very easy to see. So that's what a radio search actually looks like. We're looking for a very narrow signal because that's what we do. So you might say it's very anthropocentric, which it is. But if it's not anthropocentric, please tell me how to look for it again. Right? We always want everyone to come up with new ideas. Because now we can only think in terms of ourselves. And this was called Breakthrough Listen Candidate 1. Breakthrough Listen is this like most of this radio SETI searches. They actually found the candidate from Proxima Centauri. I think that was 2020, 2021-ish. And how it works is you look at the target for some amount of time, usually 5 minutes or 30 minutes. So that's the top. And you point your telescope away for 5 minutes, just a tiny bit away. And then come back. If a signal is present in all of these beams, that means it's a terrestrial signal. Because you're pointing at one part of the sky, it's there. If you're pointing here, it's there. Then it's radio frequency interference. That's what we call it. It's like 5G. But if it's not there in the off beam, like that's a target that's on and that's off, then the signal is coming from the on direction. Then that's the signal we're looking for. And that's what happened here. We have a signal in the on beam. And then in the off beam, it's not there. In the on beam, it's there again. So we found aliens. Very happy to announce that. But, well, first, it's definitely an extraterrestrial signal. It's not from Earth, but it's actually from an orbiting satellite.
So,
So, well, it happens. Yeah, but the good thing is you can get a lot of papers from this. Yeah. So that's how we do the search. We look at the target, we point off, and we just go back. And normally, as you can see, it's like half an hour to an hour of total time. Because there's so many stars. There are thousands of stars like within a couple of parsecs of us. And which are you gonna search? If you're gonna search all of them, you multiply like 1 hour by 1,000, you get thousands of hours. And you're going to a telescope to get many thousands of hours to search like ETI, and you're like, are you crazy? Right. So a Green Bank telescope is a 100-meter like steerable telescope. It's the largest one right now. Breakthrough Listen pays $18,000 per hour. But they have like $1 billion. Yeah. Most of the time they have to pay $18,000 an hour. And because we have so few telescopes, like we can't have thousands of telescopes, right? We can only focus on one target for like 15 minutes, half an hour, maybe an hour, for most of the time. So that's bummer. But after most SETI searches, what people do is say, we didn't find anything. Otherwise, you heard about the detection right now. And what they do is they set the upper limit of their detection. So in the y-axis, you have the strength of the signals. X-axis, that's just nothing. Don't worry about that. And you have signals that just range through all of the y-axis space. And natural objects will have very low values. There will be some anomalies, extreme cases. And there are also like very interesting SETI signals because they might be aliens, they might not. And since we established a search of upper limit here. That means we didn't find anything upwards of that. So that's our upper limit. There's definitely nothing above that. So if we don't find anything, we can at least publish something and say, wait, lower the upper limit to this, and there's nothing above that. But the bad thing is, the upper limit is still way above Earth technosignatures. So Earth is way below this line. And that means we can't detect any Earth-like civilizations. Another thing you can do with a SETI search, assuming null detection, is you can express your search in terms of this cosmic haystack. There are a lot of things. Basically, you can say, this is a power range we're sensitive to. This is the frequency we're sensitive to. That's the direction we've looked. That's the total time we've looked. And you combine all of that 8-dimensional space. We've searched this much of the entire universe. And if you assume all of the galaxies like Earth ocean, we search like a bathtub. So we haven't found any life. What does that mean? If you search a bathtub, you don't find any fish. So you can safely say there's no fish in the ocean. Right. So all of the searches are just trying to search a couple more at a time until we search all of them. And here's the list of technosignatures that we can search for. Narrowband radio, optical laser, or infrared. They're like traditional SETI in a sense. And they also have artifacts, like this laptop. If you were to find this laptop on Mars or on, say, Europa, that's interesting. If you were to find gases like CFCs around another exoplanet, then maybe they also use air conditioning. There's also like megastructures, Dyson spheres, so they're like giant solar panels around the star, and you're just trying to get electricity. We do have a Dyson sphere like Earth because we have solar panels in space. And I think our Dyson sphere completion rate is like 10 to the negative 16th. But we do have a Dyson sphere. Yeah. And there are other things like gravitational waves. Maybe when a spaceship accelerates to like speed of light, then we'll create a lot of gravitational waves. And we can search for them with LIGO or LISA. No one has done that yet. It's pure theory. And in theory, they will generate gravitational waves. But how we search for it is someone can do it. Neutrinos. Maybe people use neutrinos to communicate. We can't. And we can't use gravitational wave to communicate either. But in theory, maybe. Yeah, this is just the multi-messenger part of my astronomy career. Yeah. Cool. So in terms of modern SETI or current SETI searches, there's a huge limitation I want to point out, and I want to solve it. And the limitation is like this. Imagine you're trying to see if an office is there. And this is perfect here, because that office is facing the mountains. It's the best view. But you have to work, right? And your way of finding out if the office is occupied is you want to see if the lights are coming out of the windows. You have to work, or otherwise people will be mad. So you can't look for like 24 hours a day. And you've calculated that you can only look for 5 minutes per day. Maybe it's at the same time. And then after you look for 5 minutes and you didn't see any lights, what can you conclude? Can you conclude there's no one in the office, like ever? Right? The time axis is so long. So when you look for 5 minutes, you can only say no one's there for the 5 minutes. And that's only assuming they also turn on their lights. In this case, lights, it's a technosignature. So maybe they have other technology that you can look for. But in this case, you're looking for lights. And 5 minutes is the limit on our observation time because you have to work. Right? Or maybe you want other offices. You're looking at every office for 5 minutes. And maybe just no one's there in that particular day. Or maybe they use laser lights that's pointing in other directions. So that's what SETI is. We're trying to find if a planet mostly has life, like currently. So we're gonna assume a couple of things. Do they emit technosignatures? I mean, we do. But do they emit in the direction that you're observing? That's really important. Now you have 4 pi steradian. And your beams, radio beams or optical beams, are like arc second, arc minutes. And you can calculate the probability of them. Right. And then there's the observation time problem. When are you gonna look? If you only look before 8 a.m. every day, you're not gonna find me in the office. If you look after like midnight, you most likely won't find anyone in the office, hopefully. Right. So that's the thing. Now, when are you gonna look? Are you gonna look just at a random time? Are you gonna look once or twice? So that will give you a different idea of whether the office is occupied or whether there are ETI on the planet. So that's the problem that SETI is facing. In a typical radio SETI search, you pick a star and you point a huge telescope or a telescope array at it, like after you get the time, of course, or you can pick. And then you observe for like 15 minutes normally. Repeat for other like thousands of stars. So we look for 15 minutes. We didn't find anything. Well, better luck next time. So we just have to look for a long time, but then that costs a lot. Because you have to look at every star for like, how many years do you think is good? If we look for 5 years, we didn't find anything, can we conclude anything? For Earth, a century ago, we weren't emitting any radio waves into space, any detectable ones. So that means for the past billions of years, we weren't emitting anything. But since like 100 years ago, we are probably going to emit a lot of things in space, assuming our civilization lives. And that's a huge if. Yeah, if you read New York Times today, you'll see more. But anyway, after a normal, like a typical SETI search, here's the conclusion. We didn't find anything with high duty cycle radio emitters. And the word high duty cycle basically means it's pointing at you almost all the time. So there are a couple of cases. Okay? It might not be an isotopic emitter and just happens to be pointing at us. What does that mean? Right? If it's a tiny beam that they found us, right? They're sending spacecraft to us. Or they might have isotopic emitters. We could do that theoretically, but we're going to use all of humanity's electricity bills. And we can do that. So that's off. That's off. Everything's off. And we can do that. So good luck asking everyone. So these things are both out of our technological capabilities. Like we are not going to just point at one star all the time. That costs a lot. And we're not going to point at all the stars at all times. That also costs a lot. So high cycle is the major limitation in SETI. Just we're looking for 5 minutes or 50 minutes. We didn't find anything. What happens next? Well, we get more funding and we look again. And the thing is that we don't have radio beacons that are always on isotopic emitters. So we can't really detect ourselves. If you put Earth around like Proxima Centauri, odds are, and most times, if you only look for 50 minutes, you're not going to see us. So that's bad. It sucks. So that's why people are looking for biosignatures. It's always on, or atmospheric gap technosignatures like CFCs. But those are really weak. Like our technology, our atmospheric technosignature, you can barely see it from Proxima Centauri. you need like more advanced telescopes. And did you have a question?
Well, just, what about like satellites that have leakage coming off of them? Is that also just would be too faint from Proxima Centauri? Because those would be pretty continuous if you have enough satellites. But, maybe I misunderstood.
Yeah, so basically, we can detect them. I think those are in terms of like maybe hundreds of AUs, maybe like a light year,
Oh,
we can see them. But those are gonna be broadband. So in radio sense, you want the flux density, which is power over frequency range. Like our 5G internet is like really broad. And also satellite, their dishes are small, so they're not focusing their powers. But we try. So that means if we only have 50 minutes, how can we detect ourselves? Right, we're gonna use this 15 minutes very efficiently for a start. And the good thing is, it's not that we can't detect our technology. We have technology capable of interstellar communication. And here's one of it. The NASA Deep Space Network. It has 370-meter dish, 934-meter dish. Those are really big. And they also have a couple of others. They have input powers often more than 20 kilowatts. So that's a huge input power. And that means if they were to do the same isotropically, they would use 1 terawatt, which is humanity's total electricity consumption. So that means, remember the number, I told you before, if we use all of humanity's electric consumption, then we can see ourselves. So it's the same here. If you're within the beam of a NASA DSN transmission, you can see Earth radio waves. And this is actually detectable over hundreds of parsecs, or tens of parsecs using normal SETI telescopes. And also, if you're a laser person, I want to introduce to NASA's deep space optical communication, which you can use to watch cat videos on Mars. If you subscribe today, first month will be free. Yeah, so they tried this technology to beam some videos, like I think from Mars to Earth, and it worked great. You can't do this with radio just because of the bandwidth. So that means our future might be optical. So it might be ETI's future, or their present. Right, so we're also designing some optical searches, which are in progress. Most of the optical laser searches are done using old spectrographs. And now we're using newer ones. It happens to be that we don't have any analysis pipelines because they switched instrument types. So I'm developing one of the pipelines, but if you have any pipelines that you can use to find emission lines, please help. Okay, so the problem is not that we can't find ourselves if we get the time right. The problem is we need to get the time right. So when are we gonna look? We can try to think about this in terms of when and where do we transmit. Right, we're just trying to find an Earth analog in terms of civilization. And we just put Earth somewhere else around Proxima Centauri. When do we expect it to transmit? Is it gonna be random directions at random times? Right, if you look at this 2D plane, Earth is orbiting the sun, and the gray dashes just represent where we transmit. So, do we do that? We actually do. So, for this, normally we use deep space radars. Like we're trying to see if something's gonna hit Earth. So that's good. But we don't know when it's gonna transmit. So we still need the log perspective.
Is this actual, like, is this a rendition of historical data of radar transmission, or is this?
No, that's coming up later. Yes, this is just a good timing. It's actually random. But I'll show you the plot later. Yeah. Well, the strength is the same. And it's in a rotating direction. For example, you're just pointing upwards. And you're just let Earth's rotation take you. And that's basically what we do with like geostationary satellites. Right, they're always up there, and we're just pointing at it, and Earth rotation will take us. So the direction will just rotate. So we also do that. It's really hard to predict because we don't know how fast exoplanets spin, mostly. So we still need the luck. How about interplanetary Earth, and we add Mars into it. We are basically always pointing at Mars. Why? Because we have things on Mars. We want to talk with them. We want to talk with our spacecraft and our rovers. So we do that. So that's actually one way of intercepting, like trying to see when we might transmit. So some people did that. Nick to say, they already submitted this paper, and this is called planet occultation. Basically, if you see a planet and another planet behind it, the planet behind it might be transmitting things to the planet in the front, and you can see the radio leakage. So that's a TRAPPIST-1 system. That's a star, and you're observing from here. So when there's a planet behind another planet, you can see the transmission. And they actually did the search, which of course didn't find anything. But okay, all about upper limits if we can't find anything. So this happens a lot in TRAPPIST-1 because it's a perfect system. Everybody's looking for it. Right. So this is actually doable. But there's a huge caveat. You need to know 2 exoplanets to time your search. If you only know the existence of 1 exoplanet, how are you going to know when another planet will go behind it? Right, and most star systems that we know of, we only know 1 exoplanet. At least the orbits of the 1 exoplanet. So that basically means that we can't apply this method to most stars. So that's a caveat, you need 2+ exoplanets. Yeah.
Does this get affected that like we mostly know of like hot Jupiters type of thing? Like because you wouldn't expect like necessarily big on a
It
planet
does.
like that. Okay.
But for now, that's the best we can do.
No, that makes sense.
When we find like a lot of habitable Earth-like planets, maybe there's nothing special about Earth-like planets, right? We find a lot of potentially habitable planets, then that will work. Yeah.
Thank you.
But we also do some other things that don't depend on the orbits of other planets. For example, we almost always transmit to our telescopes at L1. The solar observatory is always looking at the sun. And the best place to look at the sun is your L1, because it's always pointing at the sun. And as we transmit to the telescope, you can see it if you're like at Earth's secondary conjunction, right? Earth, sun, and there's the beam.
I mean, the sun is also very broadband radiator, right?
Not in radio.
No, okay, I'm
Yeah, stars are normally very dark in radio. So that you're not going to see stars.
I think I get this kind of fixed direction. It's a thing, but it doesn't have to be
I'm sorry, can you repeat?
It could be anything, it could be L4, it could be L2, and still have the constant denominator. Still be some point in spacecraft and some point in just be an angle
Right.
straight up.
So this,
So why preferentially L1?
because you can expect when that one happens. That's during the conjunction. And we don't put anything L3 and L4 or L4 and L5 because there are a lot of asteroids. They're stable when you put it in there. It's very hard to put things in those two, and there are a lot of asteroids in there. Yeah. So from a technological perspective, engineering perspective, I think there might be a preference for L1 and L2. I'm not sure, but that's what we do. But we also do L2, GWST, right, and Gaia, and other telescopes. So, and you can observe this around Earth transit. Right, if you imagine that's the sun, Earth, L2 is always there. So you can time your observations during exoplanet transit. So we're gonna actually look at the actual transmissions and see what we actually do. So that's the transmissions that Jensen did since 2005. Oh, the color, how strong the color is, just means like how much time we will transmit to that pixel compared to all the transmission time average over the entire celestial sphere. So we transmit to that circle ellipse for like 1,000 times compared to a random direction. That's from 2005. We transmit a lot to near L1, which is not exactly L1, which is there. That's the sun. And that's because from our engineering perspective, it's really hard to put something exactly at L1. It's unstable. So we always have an orbit. So maybe ETI also does that, and then it's really hard to search. But at least we transmit in that general direction 1,000 times more than all the other directions, like the average direction. So that's from 2005. But what if we,
Is there a reason why it looks like it's a square? Like,
I think that's definitely another spacecraft. I'm not sure which one it was, but it might be Discovery. So there are a lot of orbits that you can put a spacecraft in around the ground points. And I guess they use different orbits just to make sure they don't collide. So Discovery is another one that looks at Earth. So L1, you can look at the sun all the time, or you can look at the luminous side of Earth. So we do that. Yeah. I have a question. Okay, cool. So if we just move time forward to 2022, and why is that important? Because JWST launching the end of 2021. So now we move the sun here. So that's the anti-sun point and anti-solar point maybe. So that's L2. And you can see this huge circle. And that's actually the insertion of JWST. So that's really cool. But you can also see that we transmit a lot in these directions. So those are our transmission to L1 and L2 in the last year or two. It's always very strong. But you can also see the other like very thin parts, right? That's because when we transmit to things like Jupiter or Mars. So this is in terms of Earth orbital phase, sun angle. That angle always changes. Like Mars might be there, but tomorrow it's gonna be there. So it's really hard to predict that, unless you know the orbits of two exoplanets, which is hard. So that's our best knowledge of what NASA does. But there's the world is also beyond NASA. There's ESA. There are other space agencies. But unfortunately, NASA is really good with publishing their transmission logs, not the others. We'll try to find them, but for now, it's all we have. So what can we do with this map once we find all the data or just with this map? Sorry, I got ahead of myself a little. So we see dense transmission to Earth, Sun-Earth Lagrange points, L1 and L2. And they can be observed during Earth conjunctions because when you're transmitting towards L1, anyone observing your secondary eclipse can see it. When you're transmitting towards L2, you can see the transmissions around transits. And you're gonna get like over 1,000 times of higher transmission time to these locations, which translates to 1,000 times higher success rate. But there's also an inclination factor, which is very hard to get. Yeah, but at least if we know the orbital phase, we can time out observations to get a way higher success rate. So this is a better way to do it. And we're not asking for a higher observation time. We're just trying to ask SETI researchers to say, let's use your 15 minutes in this way. It's similar to random. If you're just going to do a random search and not care about this, that's fine. But why not just do it this way? Right, just schedule your observations based on exoplanets or orbital phases. So that's what we can do. We can do a couple things. First, we can define Earth transmission zone, a radio transmission zone. So there's the concept called Earth transit zone. That's where you can see Earth transit. And that's basically during transit, you can find Earth biosignatures or atmospheric technosignatures. So in this sense, we can find Earth celestially targeted technosignatures. So that's a new concept. And we can also see which stars can see our transmission. Maybe in the past, as in the future. There will be a lot of stars. Our calculations with the normal star density will get us like at least a handful of stars that already saw our transmission and could reply back. And there will be way more in the future. And so we can compile the list of stars that can see our transmission and might reply back. And we can search during their reply time. And there's another thing. We can use this to guess when ETI may transmit. If they're like us, if they have astronomers who want to study their stars, their planets, or like GWST, right, they're going to put the same kind of telescopes. It might not be named the same, I think, but they're going to put similar telescopes at Lagrange points, and then we can look for those. So we are going to do a search with the Island Telescope Array, which is a grid array that's specifically built for SETI. It's of course privately funded because government really doesn't like spending public money on SETI. So we're going to focus our attention to stars with planets in their habitable zones, and we're going to search in their conjunction, basically. And we can expand it to all the other planets in the future. But for now, we know a couple of planets in their stellar habitable zone. So we can do that. It's really doable. And like I said, ETIs might want to watch cat videos on their planets. So they might use optical communication. So we're going to do a laser SETI search. NASA and Elon Musk, they're trying to use optical communication. So maybe ETI have their own Elon Musk. So we're developing a laser search pipeline to be used on modern spectrographs with fiber-fed instruments. For now, we're still doing that, so I don't have much to share. But we expect that we can find Earth-level transmission, like kilowatt level transmissions from other extrasolar planets. So that means we can still find Earth transmissions if we time it right. So that's why timing it right is the most important part. Because the time axis is so long. When are you going to search? Right. To sum up, SETI searches can really detect our technosignatures if it's timed correctly. So we use NASA's DSM transmission to see what our transmissions looks like, and we really made the bold claim that ETIs are all like us. And so we'll schedule SETI observations during those exoplanet conjunctions and see if we find any. And that's my talk.
Questions for Pinchen?
So my first one is, get past the problem of timing for some of your best candidates. Do you try to observe them in all of their phases though, as they're going around in order to, as you say, get over the problem of people working from 8 to 5 or whatever, some like fraction of that amount of time. If you build up statistics, right, if you observe enough just with one.
Are you saying the future search or?
Yeah.
Okay. We're definitely going to do some optimization based on some characteristics of the exoplanets. But if their orbits are just like hours, which means they might not be in the habitable zone, then we can do like a long search. Or if they're in the habitable zone, we can search for like hours around their transits or their secondary conjunction.
So it's still very dependent upon the orbital period in general, and you have to be cognizant of that in your cycle time to how much to observe.
But if you only have 50 minutes.
Yeah.
Yeah.
And sorry, my second question is Starlink problem for, have you guys found out that it's a problem for you guys? I do low frequency stuff, and it turns out it emits at 25 megahertz, which is really bad and illegal, but Elon Musk doesn't care, so.
Yeah, in space, I don't think there's any law you can shoot things down. What are you gonna do, right?
Yeah.
So yes, it's a huge problem. So in terms of like, so it's a huge problem for all of astronomy, basically. It's not just SETI. Like, if you're talking to optical astronomers, they'll tell you that I have this streak mass spectrum, right? So that's the problem with lasers. In terms of radio, yes, they have like huge bandwidth, and that's just like saturating the entire spectrum. But mostly, like Green Bank Telescope, they're trying to work with Elon Musk. And he's pretty cooperating in that sense. To say we're observing between 1 and 2 gigahertz. Can you not do any transmission in that bandwidth now? And they're like, sometimes, sure. And
Surprising.
and sometimes they're like, people paid us. Right? We have to do it. So there's something I think called shared bandwidth or something radio astronomy. Basically, you work with these commercial radio satellite companies to share the bandwidth.
That's actually what I would. My thesis. So if the thing is called National Radio Dynamics. So what you're talking about green bank is the types of which are taking no transmission at all. Either.
Right.
See all the wow. It's solving the problem. So what they're moving towards is natural radio dynamics, which is exactly. So don't when we're doing observation, looking in direction, move your beams from satellite off to a different direction. Temporary. So
Right.
have maybe some interruption in service, but no interruption in service, it's just microseconds. So you can facilitate it.
Yeah, but also you're not looking at the entire radio spectrum. There's always a range.
So you talked about you're developing a search for lasers in like more modern fiber spectrographs. What's the special difficulty compared to like previous searches?
So previous searches use slit
Yeah.
spectrograms. There's no difficulty per se. There's just their analysis methods don't work on fiber spectrograms.
Yeah.
So now you have tens of thousands of stellar spectra that you can search for laser lines, but you don't have instrument like
So
the pipeline to
it's
search it.
just so new that it hasn't been like developed. yet.
Other questions?
What are your, so it'd be a lot easier to detect aliens if they were constantly beaming something at us, right? But obviously we don't do this. What are your opinions? Should we or should we not, like, be beaming things at other stars?
Yeah, so there's a thing called METI, and that stands for messaging ETI. So we are actually beaming things at ETI. As you can see from the DSM transmissions, it's detectable. There are other private missions that are beaming. Can we control them? Right. So there's a huge ethical
Yeah.
debate about this. Like who's representing whom? If you're beaming, are you representing Earth? Is 1.76 meters the average height of everyone on Earth? Right. So it's definitely excites caution. Excites caution. It's
And it's not just ethical too, it's a security risk.
Oh, yeah.
Yeah, like dark forest thing or whatever.
regarded problem.
Yeah.
But some people think ETI, they're always benevolent. Some people think they're like always bad. It's just like political science.
Yeah.
People have their own opinions.
Contact actually has a nice treatment.
What?
Contact actually has a nice discussion on this.
Yeah.
Where they're like, if you're transmitting for why do you assume every extraterrestrial civilization is going to be violent? Scientists ask why do you think they're going to be. I'm sorry, scientists ask why do you think they're going to be violent. The military asks why do you think they're going to be benevolent. And I think the line that I take away from the movie is that for them to come over here and then destroy Earth would be like you going out of your way to kick an ant hill. And then the general follows up with, it's an interesting analogy of it. And how quickly do we think an ant hill and you know?
So we're not transmitting a lot. We're not transmitting like omnidirectionally, which is good. But we're still transmitting. Yeah. So Earth is doomed.
Yeah.
We did that on Mars.
Any other questions?
Yeah, I think that the Brady here is a professor, and he's always looks at the magnetic fields in order to protection. But then we have Alan Stern here, Sweary, and he thinks that there may be life in ice worlds and ice worlds under the ice. It's, but are there some other signals that we can look for kind of selective the planets that for life?
I'm sorry, I don't think I catch the question.
I just think certain signals that we look for, maybe magnetic fields around planets or something, some other chemical signals close by that might give us indications that there's something.
Yeah, so this is like in terms of normal, like biological life that might not have technology or both.
Probably not the technology.
Okay.
We don't-
Yeah, so biosignatures, the big problem is it's really ambiguous. Like there are so many things life needs. If you only find one thing, say oxygen gas, you find a pure oxygen atmosphere, which is not good, but if you find it, then you still can't say there's life there. There's so many other things that plays a role. And if you find things like in actual biology called CHNOP, C, H, N, O, P, S, the 6 elements that life needs. If you find all of the 6, it only means that there's potential for life. So biosignature is really hard to say there is actually life. And there are also things like magnetic fields. Like in actual biology, yes, magnetic fields prevents or protects Earth from like all the high energy rays from like tropical regions to some higher latitude. But there are also studies that says from the poles, the particle escape rates, like the number of particles, are actually the total rates is actually larger than if it would have been without a magnetic field. Because the magnetic field is directing all the solar high energy particles towards the poles. So we're not sure if magnetic fields are really that important. And also like icy worlds, I think they're great. And you have the ocean, like the ice that protects you from everything, but you kind of need to go onto the moon or planet to find it. Right, biosignature is often you need to go there. That's why NASA is looking for Martians on Mars. Instead of doing radio SETI search, then NASA says you shall not look for Martians. So they say, okay, we'll go there and look for Martians. It's more expensive, for sure.
Any last questions? Who would say?
We have Rachel Hatton.
Hold the screen for a second. Check 2 questions. Transmission Earth garages. Is the garage or the part of the satellite stationary
It's super low. frequency.
Theoretically,
It's
yes.
really good.
If you
So-
park at the points.
Which is.
So does that mean that if we are transmitting from
That's
Earth
what
to one of our stationary satellites, the guy way on the other side of the galaxy,
Yeah.
that's the direction.
Yeah.
light speed goes on
Okay.
with the garage.
But we know where it produces it.
If you assume that there are a lot of satellites all the way around, any of the garages or anything in that order.
Yeah.
It's gonna be transmitted to.
Right, yeah. Exactly. That's yeah. But it's all very.
Also, like, in which order?
Longer.
In which order?
You got
It's all of one.
a garage.
Yeah, look it up.
Garage is above equator. Am I wrong?
It's on their spot.
Yeah.
Those birds. Like,
Yeah.
I know that he's transmitting somewhere in the sunset.
Yeah.
Rachel, I'll see next week just to make sure they're right. Very often.
Okay.
So you can't actually, you can't put anything back.
Okay.
Like other,
It can be like this.
Yeah.
So it's always around.
I think it's, yeah,
So it's
but
always
I haven't.
very close to the.
Yeah.
Yeah.
So
Yeah,
it's
they're-
process that you
Yeah,
can-
they're making plans for us. I think you manufacture.
Yeah, I know.
options.
Because we're talking tomorrow.
Yeah.
Right.
Yeah, but we can get more food. We don't get it.
There's probably, just
Their Earth is talking about it.
and then shoot it up.
Don't work it.
I wait for Mars. And their Mars eclipses their Earth. And so there's a signal. Is that why?
But that's why-
I'll do it on Thursday, because I think she flies out on Friday night. Sorry.
I'm way out here, so.
Thursday.
You want?
That's more. So if you're seeing.
Okay.
Yeah, I can double check with her.
Yeah, you don't know, okay, I can have for her. Yes. The word that have she put all of it. Okay.
Conjunction is when
I don't need that.
The planet's not transmitting to the sun. I'm down here. I hear this guy. Okay.
If you're here.
It's actually quite.
Wow. Okay. Now, I'm waiting on bated breath for the, I really want to see what it is.
If I'm just looking at a planet, on the time, it's right next to the sun.
I think it's probe though. It's just- Yeah, I'm pretty sure it's only, look at the times. So that's.
Lighting would be.
Another 7 years.
But still, the beam is darkens.
Yeah,
And
yeah.
you know, stars are almost always dark.
Yeah, it's basically stuff.
But as it settles.
And one other little thing
Yeah.
you were talking about, or you said that, but there were several different reports, anywhere between 1.1 and I think was it 10.1 gigahertz. Nothing found. Was that band also the quiet band? Okay.
Yeah, world, yeah, exactly. So that's one of the good questions is like.
Okay,
are
but the noisy band, if you're searching
like
like.
so atmosphere. The moment you have them chemically together, they just diverge. You need a lot of time for
Cell phones,
you need
running
random
that band.
accidental mutation or something. There's some chemical process that's very likely to happen or something.
Wi-Fi is like
Then-
2.4 or 5 gigahertz.
Okay.
But
So that's because we use them. Well, that's why we use them.
yeah,
They're transparent.
Spot.
That's why we use them.
That also says we've listened to many directions, many planets,
Thousands of
and haven't
stars.
heard their Wi-Fi.
Their Wi-Fi is very weak.
Yeah.
Okay, so the Wi-Fi is so weak that we can detect.
All right, good. I actually understood some of that stuff.
That's good.
Great thought. This was good.